You're learning to program because you want the computer to do the heavy, repetitive listing for you. That is the point of writing code. This graphic shows the structural blocks of all software. No matter how complex a program gets, it is built from three specific constructs: sequence, selection, and iteration. Sequence is simply running steps in order, one after the other. Selection is having the code make a decision based on a condition, the if-then statements. If you have written basic scripts, you already use these two tools. Then there is the third construct, iteration. This is a mechanism for repetition. Instead of writing out every single action, you write an action once and tell the computer how many times to repeat it. Iteration changes the way a programmer approaches a problem. It shifts the focus from managing individual lines of code to managing the logic that governs them as a project grows in scope. Consider a common beginner scenario. You need the computer to output the word hello 5 consecutive times. This code shows the brute force sequence approach. You manually type the exact same print command on 5 separate lines. There is an immediate appeal to doing it this way. It requires no planning, avoids complex syntax, and solves a small problem instantly. The flaw in brute forcing is scaling. If the requirements change and you need to print that word 100 times, your 5 lines of code turn into a massive scrolling wall of text. This creates operational consequences. Every extra line is another chance for a typo to slip in. The code becomes difficult to scan, and updating it becomes a manual, repetitive chore. While brute force works for quick, disposable scripts, relying on it creates a structural vulnerability for any project that needs to grow. The alternative to the brute force trap is the count-controlled loop. This diagram illustrates the mechanics. A for loop uses a counter variable to track progress, repeating a specific set of instructions a fixed number of times until the counter reaches its limit. This block shows the result. You condense that wall of code down to roughly 3 lines. You set the start point, the end point, and the action to repeat. That efficiency requires a trade-off. You have to move past plain English simplicity and learn strict programming syntax rules. This text shows a specific syntax quirk in Python. The range function stops counting right before the final number you provide. To run a loop 5 times, the code must specify a range of 1 to 6. The upfront effort required to learn these exact syntax rules gives the programmer the ability to scale their code instantly. Real algorithms rarely use just one construct. They combine them to build more complex logic. This is called nesting, placing one construct inside another. Most common rule, this involves placing a decision-making selection construct inside a repeating loop. This code block demonstrates nesting. The algorithm counts from 1 to 5, but on every pass it makes a decision, checking if the current number is greater than 3, and outputting big or small based on the result. Indentation controls the logic. Everything indented under the for command repeats on each pass. Everything indented under the if command only runs if the condition is met. Nesting gives an algorithm dynamic decision-making power, but it also increases the cognitive load required to write it correctly. A single misplaced indent or a backward less than sign will break the logic. This is why programmers often test their logic on paper before they hit run. A trace table is a professional tool for predicting outcomes and debugging nested logic without relying on guesswork. The structure is simple. You assign one column for each variable and use one row for every pass of the loop. In this example, we are tracking a running total. On the first pass, the count is 1. The starting total is 0, and they combine to create a new total of 1. As we track the second and third passes, the variables update continuously. The total grows as the counter increases, letting us see exactly how the data shifts. The final row shows the predicted outcome. We have proven the algorithm functions as designed before the code has even been run. Beginners often try to hold all these shifting variables in their head at once, which frequently leads to broken code. Drawing trace tables is an upfront task that saves time during the debugging phase. These are the 2 distinct coding mentalities: Algorithm A, using repetitive sequence, versus Algorithm B, using iteration. We can judge the quality of these algorithms using 3 metrics: their overall length, how easy they are to edit, and their visual clarity. This comparison shows what happens when requirements shift. Both algorithms worked for a list of 5 numbers, but now they need to output 100. Algorithm B is more efficient to edit. Adapting it to a larger scale requires changing just one digit in the loop. Algorithm A requires 95 lines of manual entry. Algorithm B also wins on clarity and length. A programmer can read 3 lines of code and grasp its purpose immediately, whereas a sprawling list of repetitive commands is much harder to process. Efficient programming focuses on the long-term health of a project. The goal is to build logic that remains manageable as it scales. Learning loops, syntax quirks, and trace tables requires an upfront investment of mental energy. Relying on copy-paste sequence coding is a trap. Efficiency comes from using iteration to handle the heavy lifting, allowing your code to scale with minimal manual effort.